Okay, well, let me share the screen again. Let's see if I can. Okay. All right. So thank Washing and an organization committee for inviting me to give this talk on large moment effective theory. And so we had a lot of fun in the last few years in trying to um, calculate the non-perturbative Parton structure of nucleons and other hadrons using lattice QCD and an effective theory. So my talk going to be organized as this. That is, I will start QCD factorization as an effective field theory, and then I will explain why partons are hard to calculate. And so then I will discuss some inspiration from Feynman. That is, partons are defined in the infinite momentum frame. And from there, we're going to try to develop a large momentum expansion and as an effective field theory, and that's what is the large momentum effective field theory is about. So then I will discuss a few applications. So I'm sure many of you have seen this plot. The horizontal axis is the cross section. The vertical axis is the different processes happen at LHC. And you can see that the cross section varies by more than 10 orders of magnitude. And so theorists has also been calculating those cross sections, and the right panel of this plot shows the ratio of theory and experiment. And if the experiment agrees with theory or theory will agree with experiment, you got 1. And so you can see that many of these dots are cluttering around 1. So to some people, it's a disappointment because we haven't seen no sign of new physics. But for other people, this is a fantastic success of the standard model. Now, part of this success deriving from the calculations using effective field theory technology within the standard model. So a technique has been used widely in those calculations called a QCD factorization. There's a 600-page textbook by John Collins and talks about those factorizations. And so I didn't list references here. I mean, there's a lot of references. And then there's also there's a manifestly formulated effective field theory called soft-collinear effective field theory, which makes very clear how the separation of factorization happens. And so there's another book called Introduction to Soft-Collinear Effective Theory, and there are many references in there. You can consult that. So basic philosophy for this sort of calculation is that all high-energy scale physics computed in QCD loop expansions. So people have been calculating to 2 loops, 3 loops, and leading log, next leading log, etc. So those calculations are critical for those comparisons. And then the all hadronic scale physics have been parameterized by low energy constants. I call them low energy constant following original Weinberg's chiral perturbation theory, because that's, when Weinberg gives the first lecture, he talks about how the effective field theory was developed around 1970s, starting from chiral perturbation theory. And so the theory is supposed to focus on something that you can calculate. Since you can't calculate, you call them low energy In fact, the low and high is a little bit confusing here, because in chiral perturbation theory, it really parameterizes the high energy physics, should be called a high energy constants. So here I call it low energy constant, really reflects the unknown low energy physics in the calculation. So what are those low energy constants? Well, There are Parton distribution functions or distribution amplitudes in some cases. There are softer functions, and there are also fragmentation functions. So these are functions that lives at low energy that this perturbative QCD cannot calculate, and so therefore we just leave as parameters. And in fact, there are infinite number of constants because they're functions. So here is a slide showing you, how QCD factorization works. So you have two proton collide, and then you have beam functions, and there are Parton distribution functions, and partons collide in the middle. And so the short distance physics can be calculated in perturbation theory. And so end product is a factorization theorem. Says the cross section can be written as the integral of Parton distribution function, those low energy constant, with calculable Parton scattering cross sections, and plus high order corrections, which you can also write down in this theory. I mean, some more low energy constants. Now, let's take the Parton distribution as an example. And those low energy constants are actually light-Frank correlation functions. So what I've drawn here is a space-time coordinate, and horizontal is direction of where hadron is moving in side 3. The vertical is the time, and then you can define Cassini plus and Cassini minus, and as combinations of space and time, as these in fact are light cone directions. And the Parton distributions are matrix elements in the hadron states involving, in this case, the quark bilinear operators, and those quark fields are living along the light cone. So this is living in the sign minus, this lives at 0, and you have a gauge link in the middle. And so this is the nature of this kind of low energy constants. In fact, in almost all high energy scattering processes, those low energy constants involving light-Frank correlation. So this kind of correlation we call light-Frank correlations, and they can be determined by fitting experimental data. So using last 50 years of accumulated experimental data, you can extract the PDFs. There's dozens of groups around the world doing these kinds of fits, CTEC, NNPDF, MMHT, etc. So Jing Gao wrote this very nice review article, talks about those fittings. And so from this fitting, you got the upper and down and Gruan Parton distributions as function of X. Again, it's infinite number of low energy constants. And so you have finite amount of data. So invariably in those fits, you have to parameterize those distributions as function of X. So then you have a few dozens of parameter, and you fit those few dozens of parameter to thousands of experimental data, and you got those distributions. And of course, in the back of your mind, you always, question that how does the parameterization bias the fit? Because it's really, an unknown function. Okay, so the goal of this talk is to discuss how we're going to calculate those Parton physics from QCD. And this is a problem has been around for 50 years, and people have been trying various kind of approaches how to calculate this, and it's a very important quantity. As I said, that the Parton distributions are light cone correlations. It depends on time, and when you have a quantum system with real-time dynamics, it involves operators like exponential minus IHT, and this thing is oscillating phase factor. And so therefore, this is a kind of kiss of death for Monte Carlo simulation, where you have oscillating phase factors. And it's also called a sign problem. And the famous example in condensed matter physics is the Hubbard model. And it has a sign problem. So that's why even today, we don't know what is the phase diagram. In other words, we can't calculate for sure what is the phase diagram for Hubbard model, whether it explains the high TC or not. And it's because the high sign problem is very, very difficult to solve. And the signals, when you calculate, are often exponentially small. However, the recent development of quantum computer raises the hope that the people can solve this kind of real-time dynamics. And in fact, I look up a website and discover a very, very new article by Kreshuk et al. And talk about light from field theory on current quantum computers. In fact, he's giving a talk in Maryland this week, discussing how to calculate Parton distributions using a quantum computer. Okay, so the other effort has been, one of which has been called light from quantizations. And it started actually very, very early back in the beginning of 70s, later 60s. And Xiaoting Chan and Changken Ma and Collins-Soper, and they consider change of coordinates. That is, take C plus as the new time and quantize the QCD. And this goes on under the name called the light from quantization. It turns out that this has been suggested back in 1949 by Dirac. He wrote a paper in Review of Modern Physics and discusses 3 different forms of relativistic dynamics, and one of which is called front form. And so the front form uses this light from coordinates. And so basically what Dirac was talking about is the light from Hamiltonian dynamics. And this route has been pursued by many people in the last 30 years or so. At least starting in 1990s, there was explosive efforts in the light from quantization. And as you can see that there are a bunch of people in the world that meet once every year, and this is the LightCon 2019. And their goal is to try to solve the Hamiltonian problem and calculate Parton distributions. However, there are well-known difficulties in this approach. One of which is so-called the zero mode. Okay, the zero mode are the modes that carry zero momentum, and certainly the vacuum are all built up of zero modes. And because of the zero modes, it makes the renormalization of the theory highly non-trivial. And in fact, you need infinite number of renormalization constants for the Hamiltonian problem. And so that makes the Hamiltonian itself very difficult to attack in the first place. And even when you have the Hamiltonian, it's still a strongly coupled problem. And so you can imagine some kind of Fock states expansion, and there's no reason why a proton with 117 quarks is strongly suppressed relative to 3. And so in this approach that no one actually has found a weak coupling expansion approach to solve QCD. And in fact, this is what Wilson speculated back in 1994, that he would like to solve QCD as a weak coupling expansion problem, like in QED. But this program has not paid off yet, after more than 20 years. Now, one of the difficulty to solve Parton physics is this analogy. You can see through this analogy with critical phenomena. Many people here knows that the Parton distribution at small x goes like x to the minus alpha. The alpha is determined by Ricci physics. And then if you Fourier transform this to position space, and so then you got the Lycon distance. So x, its Fourier conjugate, is the distance along the Lycon, which here I call them lambda. And so you get a Lycon correlation goes like lambda to the alpha minus 1. So this is an algebraic correlation. In other words, that when lambda gets very large, it does not decay exponentially. And whereas for any normal many-body system, the correlation function should goes like exponential, and with c defined as a correlation length. And so if you look at this Lycon correlation function, which goes, decays algebraically, it tells you the system is actually at the critical point. And so you try to solve Parton physics in infinite moment with infinite momentum, and it is a problem with the infinite correlation length. So it's like you try to solve the critical phenomena exactly at a critical point. And that's where the correlation length diverges. And in fact, no condensed matter theorists directly solve a system at a critical point because you don't know how. And many, many degrees of freedom are strongly coupled and correlated, and there is no approximation basically for you to make. Well, there is a lattice QCD, and lattice QCD is the only approach so far that we know how to solve non-perturbative physics systematically, and itself is an effective field theory. However, the lattice is a Euclidean field theory, and it does not involve explicit time, or the time here is actually an imaginary time. So therefore, you can't really directly use it to solve a Minkowski problem. And what people have been doing in the past is to calculate the moments of Parton distributions. Basically, you Taylor expand the Lycon distance in terms of derivatives of operators at their origin. And so therefore, when you look at the moments of the Parton distributions and they become local operators, they lost the memory about time. So when you look at the local moments with no memory of time, so these things can be simulated on the Euclidean field theory. However, the approach is only limited to the lowest few moments in practice. And so far, people have been doing 1, 2, and 3 gets difficult. And there's another problem with that. That is the moment approach only works when you have like collinear PDFs. There you take moments, it becomes a local operator. But there are many other low energy constants or Parton properties cannot be related to local operators. For example, the transverse moment dependent distributions, soft functions, some kind of beam functions. And you can never form the moments and collapse the Lycon into moments. And so in this case, then the lattice become powerless because you don't have a local operator to work with. Now here I'd like to discuss a alternative approach of moments to how to calculate higher moments through the non-local correlators in Euclidean lattices. So basically people thought about maybe you can do some deep lattice scattering on Euclidean lattice. So you directly calculate the current correlators. And so people have been doing this since the later 1990s. And the first thought of this as like, you calculate hadron tensor, because of course, hadron tensor involves the dispersive part of this. So you have to do analytic continuations. So you calculate the current correlators, Euclidean correlators. If you want to get a Minkowski one, you can do analytic continuation, or you can take that as a Compton amplitude, and you can do compute the higher moments. And in fact, this approach called OPE without OPE, suggested by Martellini and collaborators, and they calculate these Compton amplitudes on lattice and expand it and extract the higher moments. And Braun and company has suggested you can look this current correlator directly in coordinate space through the OPE. And so in this way, you can also get higher moments by calculating non-local correlators. Okay, so now I'm gonna discuss this, the large momentum effective field theory approach. And I'm gonna start from physics motivations, because many of the approaches that people discussed in the past concentrating on, for example, in lattice calculations and tricks, try to get kind of operators you want. So here I will focus on physics pictures. So when Feynman proposed the Parton model, he was studying the deep elastic scattering, the electron-proton deep elastic scattering. And this process is, in fact, is a continuation of many similar processes people have been studied in the past. So in early days, people started with electron scattering on atoms or condensed matter systems, and you knock out particles in those systems. And the modern day method in condensed matter physics is called ARPAS. So you have photons and kick out an electron, you measure the momentum and energy of the electron coming out of this, or you can use neutron scattering on liquid helium-4 and to learn about the momentum distributions of helium atoms inside liquid helium. So people accumulated a lot of experience over the years for this kind of knockout reactions. So Feynman basically says, well, we can basically use the analogy of this. In the knockout reaction processes, and what people measure is called the momentum distributions. And in fact, like in the liquid helium-4 example, we wanted to know whether there's a Bose-Einstein condensation, whether momentum could be concentrated at k equals 0. So you wanted to measure the momentum distribution of the system. So let's start with a very simple system like hydrogen atom. So the electron's momentum distribution in a hydrogen atom is related to the wave function in momentum space squared. And if you expand this in terms of coordinate space wave function, and then you see that it's just a correlator of the wave function in coordinate space, and then you Fourier transform. And if you make an analogy of this in many-body system, and then you would promote those wave functions into operators, and then you have a ground state expectation value. So you're looking at a Euclidean correlators in the ground state of a many-body system. And so therefore, these kind of momentum distributions, they are calculable using Monte Carlo simulations. In fact, some of the nuclear physicists have developed so-called a quantum Monte Carlo method, calculated like carbon-12, 12 quantum particles. You can calculate momentum distribution in this system, and you can use it. In fact, it should really call it a classical Monte Carlo method, because it's a classical Monte Carlo application to quantum systems. They call it a quantum Monte Carlo, but they're essentially simulating this kind of Euclidean correlators and to get the momentum distribution. Now, when you deal with DIS, deep elastic scattering, we know relativity is very important. And When the relativity is very important, we need to ask, what is the difference between a relativist and non-relativistic systems? And there is one very important difference. In condensed matter systems, it turns out in those kind of knockout reaction processes, the energy transfer is usually very small because the energy transfer is related to 1 over the mass of the particle. And the limit of mass go to very heavy, so the energy transfer goes to 0. So basically in non-relativistic many-body systems, it's the momentum transfer, a 3 momentum transfer. That's what's important. Now, in the relativistic systems, of course, you have different Lorentz frames. And the virtual photon in DIS, their energy and momentum are frame dependent. So if you want to make an analogy with non-relativistic scattering, you want to go to a frame in which the energy transfer is equal to 0. In other words, the photon carries no energy. And when photon carries no energy, carries only the special momentum. This is the analogy to the non-relativistic scattering. And in this frame, then the momentum of the nucleon or momentum of the target is well defined. And in fact, in this frame, the momentum of the nucleon can be proportional to the Q, that is the momentum of the photon. And if you take the Bjorken limit and let Q go to infinity, then in this case, the momentum of the nucleon has to go to infinity. So that's the difference. So if you wanted to have the photon moment energy equal to 0, then you have to work in a frame that your hadron moves very fast, okay? And in non-relativistic systems, you can get both. You can have 0 energy transfer for the probe, and also the system is at rest. But here, you cannot. You have to have the system move. So therefore that in relativistic system, not only you need to have a momentum distribution, but you also need to have a momentum distribution when the system moves. When the system have an overall momentum PZ, the momentum distribution can depend on this PZ because of relativity. And so different relativists, a system moving with different total momentum, they will have different momentum distributions. And another way of saying this is that the Hamiltonian is not invariant on the boost. And so therefore that in a different frame, you would have a different momentum distribution. And then Feynman took a very, very bold assumption. That is, let's assume that the PZ go to infinity limit. That's what's required in the Bjorken limit. And let's take a infinite momentum limit of this momentum distribution and assume that limit exists. And then you would have a distribution called f of x. And x, of course, equal to kz over pz. Kz is the momentum of a constituent. And if that limit exists, this goes to the Parton distribution. And so this is the Feynman Parton distribution. And usually textbook did not go this elaborate details. But that's what is the Feynman's momentum distribution or Feynman Parton distribution is. Okay, so what I'm trying to say here now is that the momentum distribution is a space correlator. It does not involve time. However, the problem is that you need to have an external state which have infinite momentum. And so I have a new formulation for the Parton distribution. That is, it is a space correlator, which is showing as this blue line here. And it's time independent, but you have to sandwich this operator between infinite momentum states. And then the light cone correlation distance here is the delicate limit of z go to 0 and pz go to infinity. Okay. And you Fourier transform this correlator, you get a Parton distributions. Where the standard formulation of partons are this red line, which is the Lycon correlations. And so the relationship between these two Parton formulations is just the infinite Lorentz boost. So when you have a line segment, which looks like a blue, if you boost it to the infinite momentum frame, and you will get this red Lycon correlations. Okay, so basically, I'm trying to undo what people have been doing for a long time. That is, let's not go to light-front correlation. Let's go back to the Euclidean correlations. Okay, so with this new way of looking at, or old way, in fact, it's not a new way, it's an old way, looking at Parton distributions, then I can start with a large momentum expansion and effective field theory calculations. So the observation is that I'm looking at an equal time correlator in infinite momentum states, and infinite momentum is hard to achieve, but I can achieve a large momentum, and I can approximate this by a large momentum. This kind of practice is in fact being used frequently by field theorists. For example, lattice QCD. We know field theory are defined in continuum space and time, and so therefore the momentum cutoffs of the theory goes to infinity. But we can approximate a space-time by discrete points, and so therefore on lattice, this cutoff is going to depend on the lattice spacing A. And in lattice calculation, people typically using a lattice spacing, let's say 0.1 Fermi, that's corresponding to a cutoff equal to 2 GeV. And that's not infinity. And we assume that 2 GeV is pretty good approximation to infinity. Same thing happens in heavy quark effective field theory. In a heavy quark effective field theory, we're going to use an infinite heavy mass quark to approximate a finite mass quark. There are people who use this kind of HQET for charm quarks. It may not be very good, but you can use that as an expansion. And charm quark only has a mass about 1.5 GeV. So that doesn't stop people making approximations. So then there is this naive large momentum expansion, okay? So Feynman assumed that this momentum distribution as a function of the external momentum exists in a PZ go to infinity limit. So if it exists, then you can make a Taylor expansion. And the expansion parameter is some kind of hadronic scale over the momentum of the hadron. And however, it turns out this limit is non-trivial in field theory. And Feynman never thought about this in the context of field theory. So therefore, later on, he discovered that actually in field theory, that limit is not trivial because, well, you have to have a field theory to support infinite momentum modes. And so the infinite momentum limit is only sensible to study in the context of a quantum field theory. Now, in a quantum, okay, so I think my slides gets a little out of place. But in any case, that this is the expansion parameter if the limit exists. So therefore, you can ask yourself, how good is this expansion? Let's assume that naively this limit exists. And so if you have a hadron mass scale is 1 GeV, and if you have a momentum equal to 2 GeV, then m over p is 1/2, and the expansion parameter is square of this. And so you get a quarter. And a quarter may not be a bad expansion parameter because, you know, a lot of people are doing large NC physics and large number of color and NC equal to 3. So people made expansions in 1 over NC. So in any case, that this is sort of, pessimistic, optimistic way of thinking about this expansion. And P equal to 2GeV may not be or a bad approximation if this expansion actually works. It turns out there's a subtlety, and the limit is non-trivial, and you cannot actually do this directly, okay? The main point is that the momentum go to infinity limit is not an analytical function, okay? And PZ equal to infinity, it has a log of PZ in there. So because you have a log, PZ equal to infinity is not well defined. And this behavior of non-latticity is due to the presence of UV cutoff. And in field theory, you cannot get around the UV cutoffs. It's always there. And in a calculation, you take a UV cutoff go to infinity. And so you're taking limits of PZ go to infinity. And then you have to ask a question that which goes to infinity first? Is a PZ go to infinity first or UV cutoff go to infinity first? So you have two possibilities. The first possibility is that the momentum is always less than the UV cutoff. That is what you do in lattice QCD, or in a sensible field theory calculation, you always want to have a UV cutoff, the largest scale in your calculation, and then you have momentums much less than that. And however, the other limit, that is, you disregarding the UV scale, you always take a momentum go to infinity limit. That is a practice when you use in the QCD factorization. That's how Parton distributions are defined. So you see the Parton distribution is defined in this particular limit, and this two limit does not commute. But fortunately that the differences between these two limits, they're calculable in perturbation theory, because the difference involves only large momentum modes in the field theory. And asymptotic freedom tells you that we have large momentum modes, and we can calculate them in perturbation theory. And so therefore we can use the standard EFT matching, effective field theory matching, to take care of these two differences. Okay, so despite the fact that PZ equal to infinity is not analytical, yet we can still make an expansion in 1 over PZ. And we just keep all the logs into a perturbably calculable coefficient function. And power corrections still appears in this expansion. And so you can calculate a momentum distribution of constituents as function of the momentum of the hadron. And then as PZ go to infinity, you have log PZ appears in here, and this piece is exactly the Parton distribution you need. And then of course you also have other the power corrections. Now the power corrections relate to power counting. So any effective field theory, you need to have a power counting. And the power counting consists of identify the scales in your problem. And then you ask, what kind of physical quantities and you have and what kind of scaling you have. So here, to be conservative, you want to identify the smallest large momentum scale in the system as PZ go to infinity. So what are the smallest large momentum scale in the system? Well, first of all, you have the momentum of the parton you're looking at, which is KZ, called YPZ. And also you have the remnants of the hadron when you take out the parton. So the remnants of the hadron will have momentum goes like 1 minus YPZ. And so therefore that your power corrections going to go like 1 over y squared PZ squared, and also 1 over y squared, 1 minus y squared and PZ squared. So you can see this expansion gets bad when y go to 0 and 1. So long as you stay away from the endpoint region, and this expansion makes sense. Okay, so here I'm going to try to explain that why this kind of expansion can be thought of as an effective field theory. To answer this question, that I have to go back to the definition of the effective field theory or effective theory. And that is what we do in quantum mechanics all the time. We have a big helper space, we cannot solve it all at once. And so therefore what we do, we split that into a P and Q space. And P is called the model space, and Q is the outside of the model space. And you want to integrate out those degrees freedoms in effective field theory. Now, it is true that the light-Franck correlations contains no large momentum scales. However, it involves light cone correlations. And if we have light cone correlations, it means that it involves all momentum range. And in fact, technically, you need infinite momentum modes to travel along the light cone. And so therefore that even though the Parton distribution, they're low energy constant, they do contain high energy physics. And so therefore that you can split all the Parton physics into P and Q spaces. The P space contains all the modes with a momentum between 0 and pz. And whereas the Q space take into account all the modes between pz and infinity. And you can take into account the modes between pz and infinity through high dimensional operators. And this is what you do in lattice QCD as effective field theory. That is, you take care of the low momentum modes through Monte Carlo, but the high momentum modes you take into account through the coefficient functions of your operators or high dimensional operators. More manifestly, we can write down an expansion for the Parton distributions in the spirit of Weinberg doing chiral perturbation theory. And so in Weinberg doing chiral perturbation theory, he expressed the physical quantity in terms of leading term, subleading term with function coefficients, etc. So if you choose a specific momentum P, and so you calculate the Parton distributions in 2 steps. First step is you try to calculate the distribution contains only modes up to pz. So that's what this F tutor is. And so you have light cone correlations, F. You calculate in terms of off-light cone correlation, plus the differences between this and that. This is the coefficient function who's taking care of the modes between pz up to infinity. And then, of course, you take also into account high dimensional operators. So you have an expansion for physical quantities in terms of large momentum. And that should be independent of the large momentum. So in this way, you see, you can calculate the X dependence. And this is quite significant because phenomenologically, as I said before, we don't know what the X dependence of PDF should be like. And we use some phenomenological parameterization or some models, and then we fit the parameterization. And we never know whether we got the function correct or not. And certainly finite number of data would never tell you this. However, in the EFT expansion, the X dependence is calculated point by point through those kind of expansion. And of course, I also have to remind you that the expansion only works in the middle region of X. That is, in between X min and X max, and only when pz go to infinity limit, and you can reach the full range and 0 and 1. And this, of course, is expected because I don't think I can calculate X equal to 10 to minus 5 in a very in a computer only worth $2 million, right? And then to access 10 to minus 5 access, I need extremely high energy collider. It's going to cost billions of dollars to get there. And theory calculation have same limitation. And if I want to go to extremely small x, I have to have a large PZ. And in this case, I need a lot more computer resources. Okay, so my time is a little short here, so I'm gonna skip the momentum renormalization group equation because the momentum density as function of external momentum obeys the renormalization group equation, and you can see that this reproduces the de Laplace evolution. So the momentum evolution reproduces the de Laplace evolution. In the case of TMDPDF, it reproduces the rapidity evolution. So therefore, all of these renormalization group equations have a physical origin coming from the external momentum dependence. Again, so let me make analogy of PDFs with our Parton physics with critical phenomena. That is, I draw here is 1 over the momentum, and momentum go to infinity, you go to the critical point, and so you access the critical point physics through a finite P. So in this case, that is just like a condensed matter physicist, you study critical point physics by looking at systems close to the critical point, not exactly at the critical point. And so therefore you have the universality phenomena that you can, when in the process of flowing to a critical point, you can choose different operators and they will come into the same kind of physics. And that's why that the liquid gas system or a magnetic system that will have the same critical exponents, and you can choose different operators or different systems to achieve the same physics. So in the last few minutes, I don't have a lot of time. So Huaxing, so you want me to finish at 10:50?
Yeah, maybe you can have like 10:55 or so. That's fine.
Okay, so thanks. So I'm gonna show you basically a few applications of this. And there are a couple of review articles out there you can find online. And so I'm not being able to do all the justices what people have done in the last few years using this LaMET expansion. So I'm going to just show you the 3 examples that how this idea can work. So there's some bottom line in this application. First of all, that you approximate light front correlation by near light front correlations. So get off the light cone is the message. So the working on a light cone is very, very difficult, at least non-perturbatively. And I know people doing perturbation theory loves light cone. So you need to get off light cone. And then you try to simulate operator dynamic correlations through fast-moving hadron states. And again, that classical Monte Carlo does not allow me to through dynamical correlations, but I can simulate static correlations, but using the fast-moving hadron states to mimic the dynamic correlations. So these are 2 very important tricks for the LaMET idea to work. So the classical example, of course, is the calculated PDF itself that I proposed that in 2013, that instead of calculating a light cone correlator, you calculate a Euclidean correlator, and then you can, in the larger momentum states, this can be matched onto a light cone distribution. And Jianwei Chu and Ma have shown that this factorization actually works to order in perturbation theory. And many lattice groups, ETMC and LP3 and LPC and also various groups in the US have used this to calculate the Parton distributions. And so people so far have done up to 1 loop matching and do the renormalization for the linear divergences. etc. So I'm not going to go into great detail. And here I just show you some of the results. And again, it's the partial results and not the complete survey of things. And it just shows you that how the momentum gets bigger and bigger, that the lattice calculation approaches the experimental phenomenological curve. And so this is one of the LP3 calculations led by Weaven, Ling. And so this is the dash lines are the phenomenological results, and the red line is coming from the lattice calculations. Second application is the TMD-PDFs and softer functions. And it took years for people really to figure out what the correct light front definitions of the TMD-PDF. And Huaxing and others have done a lot of work in calculating this to high order perturbation. And people also have been busy trying to figure out how to calculate this on lattice. And LaMET formulations are mainly done by a group at MIT and also my collaborators. And the people discovered that Collins-Soper evolution conals, in this case related to rapidity evolution, can be actually be calculated non-perturbatively. And my collaborators have found that the softer functions, key ingredients in this can be calculated. Now, the critical results of all these studies is a factorization formula. That's something you can calculate on lattice. Okay, this is the so-called the quasi-beam functions, and you calculate it on lattice, and then you can match onto the experimental TMD distributions. This is defined in the particular, MS bar dimensional regression minimum subtraction schemes. And so this is softer function can also be calculated on lattice, and the evolution kernel K can also be calculated on lattice. So this is three important ingredients in this formula that you can do the lattice calculation. This can be calculated in perturbation theory, and this is what we want to compare with the experimental data. So you can see that this is extremely elaborated method. It allows you to get the quantities you want to compare with experimental data. So I'm not going to talk about how to calculate the Collins-Soper evolution conal that the MIT group have done a lot of work in this. And then this calculation is relatively easier, but the softer function is a bit hard. So the softer function involves a cross-section for two fast-moving charges and radiates lots of softer gauge particles, photons or gluons. And so you look at cross-section for this, and Huaxing and friends have calculated this to the 3 loops, and it's a heroic effort. So we think about how to calculate in a non-perturbative region, and we propose 2 methods how to calculate this. Again, using LaMET is that how to replace this Wilson line and a light cone with a fast moving hadron state. So anyway, that I'm going to be very brief here. And so this is the Collins-Soper rapidity evolution calculated using lattice QCD by the MIT group. And this is the softer function calculated by a group in China. And you can see that the people started getting those functions from the non-perturbative approaches. Finally, I want to comment that you can realize the dream that light front quantization people have been trying, that is to get all the light front wave functions. And so Brodsky wrote this extremely long review that point out of how to do light front quantization and to get those. And we have found a formulation that on lattice, how do you get those light front wave functions by calculating correlators, equal time correlators, and match onto the light cone distributions. Okay, so I think it's time for me to stop. And the partons, what I'm trying to tell you is the parton can be calculated on lattice using large momentum hadrons. And so long as the momentum is much bigger than the mass of the hadron or lambda QCD. And we're getting to LaMET 3.0, we can expecting 5% errors in the middle region of axis. And people have done two loop matching so far and hasn't been widely used. So far, most of calculations around PZ equal to 2 GeV. I think in the near future, people should be able to do 3 GeV, and with improved non-perturbative renormalizations, and in a decade or two, maybe we can expect a 1% accuracy for distributions. And finally, I want to say that nobody knows how to calculate fragmentation functions, which I mentioned earlier, and it would be great that we can figure out ways to calculate this. Thank you.